Let's see what our friends are up to now. Today, they have helped us learn a lot. Our friends are fascinated by this telephone toy of little kids and have started a new scientific topic. I think these three are really going to be great scientific inquirers. Ravi says,
"Do you remember that even we made this in our arts class a few years ago?"
Neha says,
Yes, we used to enjoy so much talking on it.
Swati says,
It still fascinates me how the sound gets from one cup to the other.
Ravi says,
Don't you remember? The sound waves travel through the string attaching the two cups.
Let me ask you now, do you remember how the sound waves travel through the string? Why don't we take a look at this string and see how the sound waves travel?
Can you see that the sound waves are traveling in a symmetric manner? Why don't we discuss some more examples? Motion of pendulum. Back and forth motion of balance wheel on a wristwatch. Motion of strings on musical instruments like violin.
Can you see something in common here? Well, in all these motions, the particle or body repeats the motion on the same path, and the time taken for one oscillation is known as the time period. Such a motion is known as a periodic motion. Any motion that repeats itself along the same path in equal intervals of time is called a periodic motion. If a particle in a periodic motion moves back and forth over the same path, its motion is said to be oscillatory or vibratory motion. In all oscillatory motions, there is a point of rest which is midway between the displacements from the left side to the right side. When the oscillatory motions have some more additional properties, these will be treated as simple harmonic in nature. The to and fro motion of a particle about a mean position on a fixed path such that the acceleration of the particle is always directed the mean position and is directly proportional to the displacement of the particle from its mean position is called a simple harmonic motion. Every SHM, that is simple harmonic motion, is therefore characterized by a constant time period t or a constant frequency nu is equal to 1 divided by t, an amplitude a, and a constant mechanical energy which is the sum of the potential energy and kinetic energy at every point in the path of oscillation.
Let me demonstrate to you simple harmonic motion of a mass attached to spring. Take a mass m and suspend it by the spring and note the equilibrium position to be O. Now pull the mass m below and leave it. This motion m is a simple harmonic motion because the force acting on m is the elastic restoring force F of the spring. Then the acceleration of m is directly proportional to its displacement x from O. This acceleration is always towards O during the oscillation.
Let's look at another experiment to demonstrate SHM, that is simple harmonic motion, using a U-shaped test tube filled with water.
Fill water in both limbs L1 and L2 and mark the initial reading of water as A1 and A2. Now blow air in one of the limbs of the test tube and notice the water level oscillating between the mean positions A1 and A2. A component of force due to gravity acts on the center of mass of the water when it is displaced from its equilibrium level. Thus, the water oscillates, making a simple harmonic motion till equilibrium is restored.
Let's summarize what we have learnt now. Any motion that repeats itself along the same path in equal intervals of time is called a periodic motion. If a particle in periodic motion moves back and forth over the same path, then its motion is called oscillatory motion or vibratory motion. The to and fro motion of a particle about a mean position on a fixed path such that acceleration of the particle is always directed towards the mean position and is directly proportional to the displacement of the particle from its mean position is called a simple harmonic motion. The periodic motion of a particle is said to be a SHM, that is simple harmonic motion, if the motion of a particle is vibratory about a mean position, the acceleration of the particle is always directed towards the mean position. The magnitude of the acceleration A is directly proportional to the displacement x of the particle from its equilibrium position. I think dynamics is a fascinating subject, don't you? We have learnt about linear, rotatory as well as oscillatory motions today. In addition, we learnt about banking of roads, artificial satellites, SHM or simple harmonic motion too. All these take into account the centripetal as well as the centrifugal forces. We truly need to thank Ravi, Neha and Swati, who have taught us how important it is to ask the right scientific questions. So keep analyzing your surroundings and don't be shy to ask questions, because there are a lot of hidden scientific wonders around us. Till next time, bye kids, enjoy.